let's look at this section of chapter number 3. What are the important equilibrium processes for environmental engineering to know? The first parameter is oxidation reduction. What is the meaning of oxidation reduction? It's a transfer of the electrons. Why we have to study oxidation reduction? Because in this process we control the fate of many organic pollutants, and of course especially heavy metals in the environment. By controlling the fate of all the organics, we know exactly where is it going, from soil to water to air, so we could control them not to move anywhere. So if you control oxidation reduction, you will control their movement. And of course, many biological reactions, once we come to biological treatment, we know that many biological reactions also depend on redox reaction, which is mediated by bacteria, by microorganisms. Of course, included biological oxidation of organic contaminant to carbon dioxide and water. So there is two half reactions that are involved here, either oxidation or reduction. Oxidation losing electron, reduction gaining electron. In the reduction equation, the electron acceptor will get an electron. We call it an oxidant. The electron acceptant, remember, this is reduction. We call it an oxidant. Take the electron to give you an electron donor. They will give you reductant. While in the oxidation process, the electron donor, reductant, lose that electron, and it will be an electron acceptor, oxidant. There are a few simple rules to remember using oxidation numbers here, that oxidation number of elements are always 0. If there is no charge at the top, it is 0. Oxygen is -2, hydrogen is +1. This you have to memorize. If you have a compound that has no charge, which means that the oxidation number of all the atoms is equal to 0, the total. If you have a charged ion, in the other hand, which means that the oxidation number of all atoms in the ion must be must be summed to the charge on the ion top. So, for example, I'll show you how could you find the oxidation state of. We know hydrogen is 1. We know oxygen is -2 by heart. Now let's find N. Remember, NH3. This is the famous chemical. And since we know H is 1, and we know here there is no charge, so nitrogen, we'll call it X plus 3 times 1, because we know hydrogen is 1, equal to 0. So what is the oxidation state for nitrogen? You can see X is equal to -3. So X is equal to -3. Same thing for S. What is the famous S? H2S, hydrogen. Remember the rotten egg smell? H2S. H2S, let's see that there is no charge here, 0. 2 times 1 plus X equal to 0, which means X is equal to -2. So we could find oxidation state by remembering a compound. In the quiz, I will give you the compound and I'll tell you to find out that atom. So there is a lot of oxidation and reduction. Like for example, ammonia nitrogen, the oxidation state is -3. This can be converted through nitrification. There is a process once we come to biological treatment. Nitrification, denitrification. This ammonia nitrogen, which has a -3 oxidation state, can be converted to nitrogen gas, N2, using the process called nitrification and denitrification to N2 gas. Oxidation state is 0, N2, remember? There's no charge here, it's 0. While this one, ammonia nitrogen, is -3. In addition, there is a lot of important atmospheric pollutants, which include NO. If you look at this N, remember this is minus 2, so this N is plus 2. So the oxidation state of N here is plus 2. And remember NO2, if you remember 2 times minus 2, that's minus 4. So this is 4. Look at this. The N in NO will be transferred to the N in the NO, which has a plus 2. It will be transferred to an N with a plus 4 in NO2. NO and NO2 conversion. You can see it went from plus 2N to plus 4N. This conversion of nitrogen to a different compound occurs through many redox reactions. So this is what will happen, and that's the control now. You could control precipitation. You could control volatilization. You could control adsorption by controlling redox reactions. Let's look at SO2, especially when there is acid rain. If there is an acid rain, which is caused by the emission of SO2, sulfur oxidation here is plus 4, it will oxidize in the atmosphere to sulfate ion. And now the problem will start, SO4 and corrosion later on. So SO2, which plus 4, it will corrode, it will oxidize to SO4 2 minus, which corrosion will happen later on. The sulfur will change from plus 4 to plus 6. Okay? So there is a lot of examples here. You should look at it, and that's for your studying. Now, we'll come to the number 2, precipitation dissolution. For example, every solid in this earth has some degree of solubility. Some has more and some has less. For example, we'll just come to the normal one that we do all the time. If we put sodium chloride, this is, you can see, solid. This sodium chloride in water, let's see, this is sodium chloride. You put it in water, it will dissociate to sodium and Cl minus in aqueous, in water. This is solid. It will solubilize. You can see it. It will solubilize the sodium. It will be surrounded with water molecules, and the chloride too. It will be surrounded by the water molecules. Now we come to something important. What is solubility? It is the maximum quantity of a substance. We call this NaCl. We call it solute. NaCl, if we are dealing with NaCl, solid, we call it solute. The maximum quantity of a substance, solute, that can dissolve in unit volume of solvent water. Water or any other quantity, any other fluid properties. So NaCl, that can dissolve in a unit solvent. This is water or H2O. So the maximum quantity of solute that can be dissolved in a unit volume solvent. Okay? So precipitation dissolution, reaction involves a dissolution of solids to form soluble species. Of course, common precipitate, you can see it, and that's happening a lot, and include hydroxide, carbonate, and sulfide minerals. And also a reaction that sometimes occur in homes is precipitation of calcium carbonate. If the water is hard, scale in tea kettles, hot water heaters, and pipes. Okay? And much of our effort here is to prevent excessive precipitation of CaCO3, calcium carbonate, in municipal and industrial settings. And what do we call this? We call it the process of removing divalent cations from water. The meaning of this, water softening. Water softening, it's the process of removing divalent cations, okay? Now, solubility, we understand the definition, but we always care about this constant. We call it the solubility product, KSP. Okay? If we know this, we can determine the concentration of the other species. Okay? Let's see. CaCO3 solids dissociating to calcium and carbonate. So KSB of this is equal Ca2 plus, CO3 2 minus, okay, over CaCO3 solids. CaCO3 solids is 1, since in the solid we don't put KSBs. So Ca2 plus and CO3 2 minus. If there is no precipitation, if you just like put this into water, if there is no precipitation, if the product of the concentration of this times this is less than KSP, then there is no precipitation, and we call this undersaturated. If the product of this times this exceeded KSP, then we could call it supersaturated. So the solid CaCO3 will precipitate easily until the product of the ion concentration equals KSP. So for every reaction there is a KSP, and of course there is a significance, hardness removal. Same thing for this reaction, there is a KSP, and you can see also hardness removal and scaling. This reaction, KSP, hardness removal. This reaction, KSP and hardness removal. And this reaction with a KSP, this is to remove heavy metals. If you have heavy metals in water, you could control this removal by controlling this reaction. This reaction is also with a KSP and heavy metals removal. This one is famous, AlOH3 solids. This has a KSP, and this we could call it coagulation. You will see this in the lab. FeOH3 solids, this is also for coagulation and iron removal, if you have iron in water. CaSO4 solids is also another KSP. This is to take sulfur from flue gas. Flue gas desulfurization. You don't want to pollute the air, so you want to take the sulfur from the flue gas before it pollutes the air. This reaction is also another one that has like a range of KSPs. Okay, so every reaction has its own KSP. So let's look at this. Let's look at this reaction. MgOH2 solids reacting and with water to dissociate to Mg2 plus and 2OH minus. Remember, here there is 2 moles. Here there is 2 moles of OH. The question is to ask you about what now? What pH is required to reduce the high concentration of dissolved Mg2 plus? We have high magnesium. Magnesium and calcium, it could increase hardness. So we need, what is pH? To reduce high concentration of magnesium. He gave you the KSP of the reaction. Okay, let's say that we have this magnesium OH2 solids. This, in reaction-wise, if you go look at the table, it's Mg2 plus and 2OH. This 2, you will see it in a few seconds. This 2 will make it square. So let's convert this magnesium to mole per liter. So Mg2 plus is equal to 43 milligram per liter, and you convert milligram to gram. So gram over milligram, this will cancel with this. And now you divide it by the molecular weight of magnesium. The molecular weight of magnesium is 24. So you divide it by 24 gram per mole. Of course, molecular weight of magnesium is 24 gram per mole. This is molecular weight of magnesium. So 24, you can see gram cancel with gram. Now you have mole over liter. So this was converted to 0.0018 mole per liter, or molarity. For the KSP, you need to do molarity into the equation. So we'll put it like this. El KSP is 10 to the power minus 11.16. So we put it here. Mg2 plus OH minus square over MgOH2 solids. Okay? Again, in KSP, we cancel this, make it 1. Remember the square? Why? Because there is 2 moles of OH minus. Okay, here there's no 2 mole, there's 1 mole here, so we put it 1, or just take it off. Now, he need to know pH, so we need to find OH first. Mg2 plus, we found it here, we put it here. That's it now. So the equation would be like this, and then we could find OH. OH minus is equal 6.2 10 to the minus 5 mole per liter. And remember, hydrogen times OH minus is equal 10 to the minus 14. So we have OH, we have this, we could find H. H would give you 10 to the power minus 9.79 molarity. Now, also we know that pH is equal minus log hydrogen ion. We have the hydrogen ion 10 to the power minus 9.79. You put it here, it will give you pH 9.79. So you have to make it all the way to almost 9.8 pH in order to reduce this high concentration of magnesium. Of course, at this pH, 9.79, any magnesium in excess of 0.0018 will precipitate as magnesium OH2 solids. So they will be precipitated down into the bottom of the tank, because the solubility of magnesium 2 plus will be exceeded. So anything higher than this will be precipitated. Okay? Now we come to this volatilization. What is volatilization? It is the transfer of a compound from the liquid to the gas state. Okay? We call it transferring from the liquid, as we just mentioned in the class. If we have water here, okay, let's say we closed it, and this water has benzene in it. So the transfer from the water to the air, we call this volatilization. And also the transfer, if you have like a solid, and this solid's transferring from solid to gas, not to water, not to anywhere, only from solid to gas, we call this sublimation. Now, let's look at this flask. It's closed. So you can see that the benzene is transferring from the liquid to the gas, volatilization. With time, you can see that, because this is closed, you can see that these gases will be all over the flask. So the vapor pressure of the flask will increase, which means the one with higher vapor pressure, which means it has a higher volatilization. The first guy who described this, his name is Henry Law, or Henry Constant, KH, which control the transfer of that organic from the aqueous phase to the gaseous phase. You can see the transfer from liquid to air, or from air to liquid. Henry Constant give you the equilibrium of that chemical between the air and water, of course, for dilute solution. So this is KH is equal the chemical in the gas phase divided by the chemical in the aqueous phase. Okay? So these are the units for each one of them and the definition for each parameter. So air water is either in mole of chemical per liter of air divided by mole of chemical per liter of water. Mole per liter of air, mole per liter of water. Again, we mentioned sublimation. Okay, we also have to mention that if you have volatilization from water to air, from air to water, it's condensation. Okay, let's look at this slide. Of course, we could see that we would accept or expect the more volatile compound to have the greater saturated vapor pressure. Okay, so let's see N-butane. The vapor pressure is 2.4 atmospheric. This has the highest volatility. While if you go to lindane, pesticide, they put in for agricultural use is 10 to the minus 6. So you'd expect if you throw this in plants, this one not volatiles. 10 to the minus 6, that's very small. The vapor pressure is very small. Okay, while here, if you put it in water, this will highly volatile. Benzene is next, and then of course water and PCE. KH has a lot of unit conversion. We need to, I need to give you this in the quiz and the exam, so you know that R should be always at this level. If you are dealing with any one of these conversion, you should follow it. Okay, later on, once we do the partitions, you will need this equation KH divided by RT, especially if KH has later atmospheric over mole. Okay, we'll stop at this point and we'll continue lecture number 4 in a few seconds.